And our next speaker, Mumtaz Vauhkonen, who is Director of AI and Head of Multimodal and Generative AI at Verizon, is going to tell us a little bit more about her work and the vision they have at Verizon related to the next steps for multimodal AI. So please welcome Mumtaz to the stage. I think you're here, making your way through the crowd that's lined up to see you. A warm round of applause.
Thank you for the introduction. Hello all. Today I will be talking about multimodal AI in an enterprise setting, how we are using multimodal AI to solve some of the complex problems we have in Verizon. Thanks for taking the time to come here this morning. So the agenda today is briefly touch on what is multimodal AI. We have been having these multimodal aspects for the last 2 decades in AI. What has changed now? And what is a typical pipeline for multimodal AI application? How does it look like? The data and the features, right? This is the most important component of it, aligning the data for these applications. And what are we doing in Verizon with it? And what are the challenges that we typically face? And what areas of focus are there for improvement for the future? So if you look at it, what is multimodal AI, right? The AI systems that can take multiple types of data, like text, images, sound, sensor channels, and so on. And similar to the way we humans perceive through multiple senses, we are trying to create AI that can be complementary with multiple types of data input. This is not new. If you look at a recent few years, we have been trying to do this with autonomous driving, incorporating the LiDAR, camera data, radar, ultrasound, other sensor data coming out of the car systems, and to be able to make a single decision or multiple decisions in a fraction of milliseconds. Like if you detect an object stopping the car, right? It takes multiple data inputs there. So if you look at how these models, the current scenario of generative AI models, you're seeing Gemini, you're seeing OpenAI models that are able to do multimodal inference. If we look at this, what is a typical pipeline for it when you're creating these applications? So you have multiple types of data, like text, images, videos, audio, and you derive features out of it. You narrow down the feature set you want to input into your problem space, and then you create embeddings for each of these, and then you create a fusion of these embeddings, and then you feed that into a model. It could be generative AI model or other models that are created to take this kind of input. Typically these days, it's generative AI models. There are very large models like the latest OpenAI model or Gemini Pro, and there are also really small models that have been piggybacking off of small Llama models. And as you know, recently Llama also has released several multimodal-based models, the latest one being the movie generator. So bringing it back to Verizon context, let's say we have an infrastructure image. We use this comes out of drone data, and then we can input this image, use encoders to extract the embeddings, and then similarly we'll have textual input for all kinds of questions. For example, after a storm, during disaster recovery efforts, we want to know how much the antenna has gone haywire in its alignment, and we want to know the tilt of it. And we also have some audio signal to test, what is the transmission, how is it going. So we'll align all these type of modalities, extract the embeddings in this manner, and then do a fusion after that. So this is a typical process. And how do we go about fusing multiple types of data? It's not one style of fusion, right? So there's a mechanism to fuse using multiple strategies. One is early fusion. You integrate these embeddings early on before any decision is made by the model or a series of models. The next one is called mid-cycle fusion. You tend to fuse them mid-cycle. Sometimes when extract embeddings, not all of them are the same. In order to correlate the features well, and aligned to a certain problem space, you have to do a latent representation. Latent representation is nothing but identifying the underlying attributes represented into a two-dimensional space or three-dimensional space to be able to correlate them on a singular profile. So when we do that, we are able to fuse these multiple modalities better in certain scenarios. And there are certain techniques where we rely on late fusion. The problem you're trying to solve typically dictates whether you're picking early fusion, mid-cycle fusion, or late fusion, or hybrid fusion. Late fusion is when you allow the model to make a decision. And then for each independent modality, the decision is made, and then you correlate the outputs to arrive at a joint conclusion. That is late fusion. And hybrid fusion is, in the whole pipeline, you're trying to apply early fusion or a mid fusion or a late fusion. You're using multiple techniques in one singular pipeline for the problem. So let's see, early fusion, as we showed here, like right after your embeddings, you're fusing the embeddings using multiple techniques. Sometimes it's simple concatenation. Sometimes it's normalization techniques and bringing them together and then feeding it into a decoder model. So I'll show examples of this application where we have applied late fusion and early fusion. So late fusion, typically you have the decisions made by each independent model that gives out results for the textual encoder, that gives out results for an image encoder and a sound. And the sound systems typically work a little bit different. If you're getting like a music input or a sound wave input, then you have an audio encoder. Otherwise, if it is just text in a video, you parse the soundtrack, do speech to text, and then feed it back into a textual encoder, and then get the embeddings, and then feed it into the model. So, so what are these multiple domains that we can apply multimodal with? If you look at the current state, it's a wide field. There's telecommunications, where in Verizon we use it for multiple purposes. We have robotic systems like disaster recovery. Now we can send out robotic systems in a mining field or a disaster recovery location. We are largely relying on image-based or sensor-based models, but once you integrate multimodal, they will be able to communicate back with you in natural language. We send out drones on a daily basis for evaluating a lot of our infrastructure. The current scenario is we bring back the drone, evaluate the data, and then feed the data into AI models. What we are trying to achieve is, while we fly the drones, we want to be able to communicate with the drones using multimodal capabilities, so we get the inference right away instead of waiting for a few hours or a day. Manufacturing, like quality checks. If anybody has been in a manufacturing plant for car assembly or product assembly, you would know the multiple stages it goes through. Having a multimodal ability would solve this whole process pipeline much faster. Teaching and knowledge, education for children or multiple needs or personalized education is another scenario. And medical analysis, combining multiple modalities would really enhance the game for diagnosis, online diagnosis or in-person diagnosis much faster. If anybody has broken your bone and been to a specialist, you know how long it takes to get out of the room with your diagnosis. This can really speed up the process once you bring multimodalities into the picture with your vitals and immediate analysis by the system. And there are several other domains. These are just to name a few. And how are we doing it in Verizon? What are all the kinds of applications we are applying multimodal capabilities? One is like a technician troubleshooting. We have antennas, we have radios, we have multiple types of FiOS network equipment in places. Our technicians go out on a daily basis, thousands of them, to fix this equipment. So when they're troubleshooting, their tasks are different. Typically, they go through the manuals, read through the manuals, to see how to troubleshoot a certain error code or equipment. Now we have AI assist systems coming in place where they can interact with a natural language to how to troubleshoot a certain system. Based on the question, the AI system automatically figures out what to surface for the technician. Either they can project a picture into it, they can type text. So they rely on this a lot. And engineering assistive bots were long-haul circuits. Long-haul circuits are, for example, let's say Europe, the telecom networks, fiber lines that run from one country to another country or one corner of the country to another corner of the country through multiple routing locations, those are called long-haul circuits. And when traffic gets clogged, the engineers have to immediately design a new circuit to divert the traffic. And for a new engineer or a less experienced engineer, it's a daunting task. So we have an AI agent assist system coming in place where engineer can use the bot to help design the circuit much faster by feeding in multiple types of inputs. And sometimes they have videos, instructions how to do this piece of a circuit versus the other. So we feed multiple types of inputs as an assistive agent. And then there are other types of applications where we want to expand our cellular network. And a lot of things go into real estate assessment, location, direction, and type of building, height of the buildings, and so on. So now engineer has to go on site, measure all these systems, manually figure out a lot of things. But by using AI, we're able to use low-flying aircraft data and also drone data to gather the information, feed in a lot of other technical aspects of the equipment, and be able to assess if that site is good enough to deploy a certain equipment with a certain wavelength. And for number 4 also, for exposure, RFE exposure, anytime we deploy our equipment, we have to make sure that we are compliant with the government rules. So this also we're able to accomplish remotely using AI, computer vision plus textual models. So what are the standard requirements for a smart assist bot? So the standard requirements are that we parse domain-specific technical content, and then we identify steps for a given query for resolving an issue. Like, it should be able to bring up tickets, documents when they're asking question, hey, what is the problem with this equipment, if there are any tickets? And it should be able to query multiple. If there's a video to query, if a technician has taken a video and uploaded it for a troubleshooting system, it should be able to query the video. It should be able to query an instruction video. And it should hold context. If you're troubleshooting, you can't have a question independently isolated, right? So my follow-up question is usually related to the previous question if I'm troubleshooting an equipment. And then also be able to separate simple prompts from complex prompts and have the ability to connect abbreviations. A lot of people enter abbreviations like QAM, 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 and a very experienced engineer would know what it is, but then AI system should be able to expand into complex audio. So I would go through a smart assist system. It's an example of long-haul circuits, and this is the type of data that can go into the system. Yes. So the below blue bars one is a small piece of a circuit to be designed, and the top one you're seeing is a traffic flow at a certain site. So to be able to develop this kind of an assistive agent, we had to parse through a lot of documents, about 10,000 documents for a lot of network manuals, equipment, training documents, videos, and so on. And a typical document would have images embedded into it, videos embedded into it, and a lot of troubleshooting steps based on the error code. And this is how a high-level architecture flow looks like for us, like pre-processing a lot of these independently. Each one, we pre-process text, image, video, structured data separately, and align the features, and then feed them to embedding models, and then do certain scenarios we have to do early fusion, and certain scenarios we do late fusion. And prompt engineering, this cannot be underestimated at all. Prompt engineering is a very important piece for multimodal applications as well, just not textual. And then the next important piece is search and retrieval systems. For text, we all are familiar with the RAG pattern by now. So how complex it can be with multiple layers to enhance the efficiency when it comes to unique domain space of your industry. Similarly, here for multimodal, the RAG gets a little complicated. You're not only indexing the text vectors, you're also indexing each frame of the video to be efficient for the system, so that when you ask a certain question, if the video is 1.5 hours long, it can pull up the frames, time segment that exactly matches your question, like video question answering system, and also brings up the right document workflows along with it, aligned with that piece. So a lot of time goes into the pre-processing part, the search and retrieval part in building this application. Actually, 80% of the time went into those aspects. So you have to plan for a lot of work there. As I mentioned earlier, we have multi-layered retrieval augmented generation system for efficient processing, like search modules, step-by-step queries. And also another thing that really helped is this tree of thought chaining and prompting to make sure that the model can clearly get inputs in retrieving the right pieces of the multimodal outputs. And here is an example application where engineers are out trying to figure out what equipment has to be deployed. Are the buildings similar? Right, so we get low-flying aircraft data. This is aircraft data flown probably about 5,000, 6,000 feet. We first pass this imagery. The imagery consists of like 1 mile amount of data looking from the top. So we run the images through a computer vision model first, extract the type of buildings we are interested in first, and then pass these buildings through an automated pipeline to understand which buildings are very similar, and the height of the buildings, the shape of the buildings, so that we know what kind of equipment can be put on what kind of buildings. For a human to cover 1 mile, 1 square mile in a matter of minutes is really hard, but this AI system can accomplish that in a matter of seconds. And we feed this, and the model gives out of, let's say these two images are similar, yes. So, and image similarity, right? This one says that it is no. So this helps us, cuts down the time by about 80 to 85% for our technicians in coming to certain conclusions. And another multimodal input is this, a technician being able to go, put a pin on an image, and get the radius and do detections of what are the types of poles present there, what are the type of equipment present there, what is the distance from a piece of infrastructure we have to the closest construction facility, and so on. And consuming all those detections, you see on the left a fully generated AI report, automatically generated by a textual model. So similarities as well, how many sections are detected, what structures are similar, and so on. So these are some of the applications we are using. And as I mentioned, gathering and preparing the right data set, you have to invest your time there. That's a very challenging piece where right now we are getting used to dumping data and expecting good answers. But if you invest your time in cleaning up your data a lot, putting the right type of data into multimodal applications, you can really scale these applications faster. The response times will be faster from these applications. And identifying the right type of models in the pipeline, what kind of a vision model or a vision embedding model, what kind of textual model, and aligning these models in a correct way. And the domain expertise, never forget the experts. They may not be the AI experts, but they know the domain well. They contribute to these AI models equally as good as the AI model is. So lining up the domain expertise also matters a lot. Yeah, this is what I have to offer in this talk. In this short period, we can go on talking about each of these for hours at a time when you are actually implementing, but at a high level. Any questions? Thank you.
Thank you so much, Mumtaz. I think we have time for one question from the audience. We have one hand up. If you can have a mic, easy to reach. I think it's on its way. You can't see it, but it's coming. Yep, coming through the middle of the aisle. One microphone for the gentleman over here. Yep.
Well, thank you. Thank you, Mumtaz, for the presentation. This was very insightful. My one question will be, how do you decide to build inside versus to buy technological components of these? Do you build everything yourself? Do you study solutions that might be a good fit? What is your approach to this trade-off?
So certain things depends on the sensitivity of the data, right? What is it that you're building? There are certain applications where an external solution will immediately solve the problem. For example, send it out to OpenAI or generative AI, right? But a lot of these applications are very sensitive by nature, so that's what we go by. Yeah, thanks.
Great. So Mumtaz, you'll be around for the fireside chat, I think
Yes.
one session from now. So we'll have you back on stage in a second. Thank you very much.
Thank you. Yes, sir.
Thank you.